Hello and welcome back to Let's Code Physics. We had a lot of fun last time setting up a drag force in our projectile motion simulator. You can see the evidence of the drag force here because of the asymmetry in the trajectories. For one, our trajectories are not lining up in their matching points. In their complementary points across from 45 degrees. But also you can see that there's an asymmetry in the arcs themselves. They're a little bit longer on the initial side, the upgoing side, than they are on the downgoing side. So that is rather different, and that's made an impact in whether we were able to make a football field goal last time. Today what I want to do, I want to make things a little bit more interesting for our drag force by adding in a wind, because the drag force is based on the relative velocity of the projectile through the air. What that means is that we made a little bit of a simplification last time in that we had no wind, in which case the velocity that goes into the drag force, so here are the two lines where we're calculating the drag force. First we get the direction of the velocity v hat. And we just put in the projectile's velocity, because if there's no wind, then that's going to be the direction of the relative velocity. But what I really need to do is I need to have this be the projectile velocity minus a wind velocity vector. So what we're going to do, back up here when we define all of our stuff, we're going to define something of a new vector for the wind velocity. And I want this to be about on the order of our projectile velocity. So our projectile velocity is initially 5. So let's make this, let's say this is going backwards in the x direction 1 and 0 in the y and z direction. So back on our animation, remember we are launching into the x direction, and so this is going to be pushing the projectile backwards along the x direction. So that's a headwind. There we go. There's a wind blowing against the direction of the projectile's travel. And so now that I've got a wind velocity, what I need to do here for the projectile, for the drag force, is instead of having projectile velocity, I need to have projectile velocity minus wind velocity. So again, this means it would be the same thing if you put in zeros for the wind velocity. We would have exactly what we had before. But basically what this is doing, this is getting the relative wind vector between the two. So if they're pointing in opposite directions, you get a greater relative wind, because you've got the projectile's forward-going velocity minus the wind's backwards-going velocity produces a greater vector magnitude here. Now, of course, this is the velocity vector unit vector, so this is going to have a magnitude of 1 no matter what. But I also need to change the velocity that goes into the magnitude of the drag force here. So I'm going to replace this thing with projectile.velocity minus wind.velocity squared. And I suppose I should help myself keep track of this, that this is the relative velocity. So let's just call that RV hat. So this is now the relative wind, it's not the relative wind velocity. What's the correct term for this? This is the velocity of projectile relative to the wind. That's the more full way to say that. I might be using the term wind velocity incorrectly there. But the point is, if these two are opposite of each other, then actually let's think of it in terms of the drag force here. If these two are pointing opposite of each other, then it's going to produce a greater magnitude. But if they're pointing in the same direction, it's going to produce less of a magnitude. So we should see our projectile fall a little bit shorter this time around. Okay, you can see that the arc is a little bit more pronounced now, right? So you can see last time they were only slightly asymmetric. Now we're getting a lot more asymmetry. In fact, you can even see in these last few, including these last few especially, that the wind is blowing the thing backwards. So here is our starting point, and our last 1, 2, 3 projectiles ended up a few spaces back from where they started. In other words, they did not have enough forward-going velocity to overcome the wind velocity pointing back the other way, and the drag force won out going backwards. So actually starting with, in this case, it looks like starting with about this one. Which one is that? So that's going to be 90, 85, 80, 75, 70, 65, 60, 55. So somewhere between 55 degrees and 60 degrees, at some point in the arc, the thing actually travels backwards. So this trajectory no longer a nice, one-to-one function. So this is going to make a Calc 1 student's brain hurt because it's failing the vertical line test for a function. So that's that's qualitatively different than the stuff we got last time, because last time we had drag, but it kept going forward. This time we've got drag, and the drag can actually be enough to push the thing backwards. Again, because we've got this constant. Because we've got this constant wind velocity pointing the thing backwards. So that's, wow, that's pretty neat. So that actually already demonstrated pretty much everything I wanted to demonstrate. Let's play around with this thing's direction a little bit. Let's suppose you had a wind velocity that was pointing downward, but let's suppose you also got a teeny tiny bit of an up current. Let's suppose this wind velocity had the same x component, but now let's suppose there's a little bit of an updraft. Let's see what we get here. So again, the leftward velocity is winning out, but the peaks are getting a little bit higher, right? Because there's a draft pulling it upward, which is nice. And then of course that's going to change our loops here a little bit. Ooh, that was neat. That thing changed concavity right there. That was pretty interesting. Let's see. And then, of course, if I make this a downward draft, so let's suppose you've got a negative y component to the wind velocity, that's going to be pushing it down even more. And, of course, we know this intuitively, but what's neat about making a program like this is that you get to test quantitatively what's going to go on with this thing and how it's going to impact it. We have a little bit of a concavity change there. That's pretty cool. All right, so this is in the context of the football code, the field goal code. So let's reset this stuff to our field goal kicking value. So we had a projectile speed of 5. Let's reset that to our average kicking speed of 27. And let's see what this wind does to our football. Oh, we are not making it. I don't think, no, none of them are going to make it at this point. Wow. In fact, they are kicking back the other way. Now, of course, that's a pretty powerful wind, right? So this is 27 meters per second, a wind of 1 meter per second, right? So that's the average human walking speed. So let's suppose we are not playing in such harsh conditions. Let's decrease this to maybe about a quarter. And let's see. I just want to see some go in and some not. Okay, we got 1, 2, 3, 4. Is the last one going to make it? That one barely makes it. That one does not make it. So let's see. 5, 10, 15, 20, 25, 30. I believe that one made it before, so this wind is enough to keep you from reaching it. So this does show you that the window of angles you have is pretty strongly dependent on the incoming wind velocity. And of course, football players know that intuitively, but and if they kick it like this, it's going backwards. Of course, kickers know this intuitively, but this just puts a nice, qualitative spin on it, which is pretty neat. Okay, so I'm pretty happy with that. I'm not going to bother turning on the angle in the other direction. I mean, it's pretty much going to do... actually, that would do something cool, wouldn't it, if it went this way and then curved back around. Let's actually do just one of those. Let's see. Let's leave the wind velocity as it is. I just want to do one loop of the angle here. Let's do a delta angle of 5, and let's hit a max angle of 6. So it'll do 2 loops for that. So first we're going to get the same results. Oh no, we're starting over this way. So what you can see, I was hoping to get it to where they would curve back around the other way, but I don't think they have enough. I don't think they have enough air time to do that. Maybe when we get to some of the higher ones, they will. Oh yeah, that's right. It'll happen at the higher angles. That's right. Just want to see something neat happen in 3D. Let's see. These are all still in the same... Oh, no, they're not all in the same line. Yeah, they are veering off a little bit that way. So that's kind of cool. So yeah, what we're going to do next, while this finishes out, let me describe to you what we're going to do next. What we're going to do next is add a lift force to this thing. So we've added a drag force. But drag forces can also come with lift forces that can help the thing sail through the air. And so that can be pretty cool to watch. So we'll be able to model, like say a boomerang or a paper airplane or something like that. Yeah, so you see them now, they are veering off to the side a little bit, so that's kind of cool. Anyway, so yeah, so the next thing we'll do in this series is we'll add lift, and we'll have some fun with that. So thank you so much for watching. I will see you next time. Bye-bye.